So this is kind of review. So an electric circuit is something that's going to do work, creating things like light, heat, things like that. The components of a basic circuit, you have to have a source, a path, and a load. And some other devices that could be part of this are what, guys?
Ms. Bush, I think you might have muted yourself because I can't hear you talking right now.
All right, so I don't know what's going on with this computer right now. So what are some other devices that can be found in a basic electrical circuit?
A resistor?
Well, a resistor is the load.
Oh, yeah.
We haven't really gone into depth in them, but you're talking about things like fuses and switches and things like that. Those are some of the other parts that are usually in a circuit. Does that make sense?
Yes, ma'am.
Okay. So what does a voltage source do? What is the purpose of it?
It provides the input to the electrical circuit.
It provides the push and the boost for the electrical circuit, yeah. And what about conductors?
They're those, like the light bulbs. They like no, that's for resistor. A conductor basically is like what helps the energy flow.
Very much so. It's what allows current flow. And then lastly, on this page anyway, the function of the load is to do what?
To absorb the energy and perform a function.
Or even more basic, it's meant to do work.
Yeah.
Some form of work. That is what it is meant to do. Okay.
Yes, ma'am. Oh, and Ms. Bush, are we going to need another textbook for this one, or are we using like the electronics electrical textbook?
Still using your textbook. What you will need to get is a lab book.
Okay, and the lab book is at the bookstore?
Yes.
What's the name of the lab book?
I think it's give me just a second, I'll look for it.
Okay.
All right, so this right here is the book that you need. It's Experiments in let me pull it up. We'll say this, don't buy the used, guys. It's not something you're supposed to be using.
Should I get the new one?
You need to get a new one, yes.
Okay.
But it's Experiments in Electrical Fundamentals and Electrical Circuits Fundamentals.
Okay.
Something like that.
Yes, ma'am.
So that's the only thing you need. The electricity electronics you should already have on hand.
Yeah, I do.
So back to what we were talking about. What is the difference between an open and a closed circuit?
closed circuit is whenever the circuit's able to flow uninterrupted, and the open circuit is whenever like a switch or something is turned off and it breaks the flow of the current.
Very good. That is exactly right. So what is Ohm's law?
It's what we use to find out our voltage, amperage, and our wattage, like our work.
Okay. So basically, to sum it up in even more simple terms, Ohm's law is the relationship between voltage, resistance, and current, whereby voltage is the push, it's what starts everything off. Current is what actually moves, and what is moving when we call it current?
Electricity.
What kind of, let me say it a different way. What kind of a particle is being moved when we run an electric current?
Electrons.
Electrons are being moved, yes. Everybody understand that?
Yes, ma'am.
Okay. All right. So what is voltage and what is the unit?
Voltage is like you said before, it's the push out of the voltage source, and it's volts.
Okay. What is current and what is the unit? So current is the flow, right?
Yes, ma'am.
And what is the unit?
Amps.
That is correct. Okay. What is resistance and what is the unit of resistance?
Resistance is like whenever it flows to like a certain point, it derates the amperage of the current, and it's the unit is ohms.
Okay, unit is correct. What a resistor is truly meant to do is hold back current or limit the current that is moving through a circuit, is the really simple way of putting that out there.
Yes, ma'am.
So here's the answers in a little bit more of different terms here. So an electrical circuit provides a path for current to flow. Closed versus open circuit is what exactly we said. Closed means there's flow. Open is no flow. Okay. Basic circuit includes a source, conductor, load, and return conductor. So source, path, and load. Exactly what we were talking about a minute ago. A control device such as a switch is included in most circuits. An OCPD, does anybody know what that stands for?
I feel like I've heard it before. I can't remember off the top of my head.
It stands for overcurrent protection device. So those are fuses and things like circuit breakers. These are very typical to be included as fuses and circuit breakers. Why? Because it protects the circuit.
Yes, ma'am.
The voltage source produces a difference in electrical potential or pressure to cause current to flow in a closed circuit. Conductors carry the current. Okay. Ohm's law is the relationship between the circuit's voltage, current, and resistance. Okay. So we have this set up again. This is again a review from intro just to make sure everybody's caught up to speed. Voltage is symbolized two ways. Most textbooks in military refer to it as E, which stands for electromotive force. A lot of people tend to put it as V because volts and volts.
Yes, ma'am.
Current is mathematically symbolized with an I. The units is the ampere with an A. Resistance is capital R for your mathematical equations, and its unit is ohms, done with the omega symbol. So Ohm's law, E is equal to I times R. This is the same as saying V is equal to I times R. R is equal to V or E over I, and I is equal to E or V divided by R. Does that make sense? All right, so if the current through a resistor is 15 milliamps and the resistor is 1.8 meg, what is the voltage?
Let me get my calculator. It's 27 milliamps.
Does everybody agree? All right, 27 milliamps.
Oh, you said mega?
I think I said kilo to begin with, but it should have been mega. I might have
Okay.
gotten
So yeah, 27 kilovolts. That makes more sense.
Yep, 27 kilovolts. That's quite a bit of voltage, though, isn't it?
Mm-hmm.
So we have I is equal to V divided by R. We start with 27 kilo ohms as the resistance. What is the current when you use 100 volts across it?
That'll be 3.7 kilo. No, that'd be 3.7 kiloamps. Or just amps.
So 100 divided by 27,000.
Oh wait, I did that wrong. That'll be 2.7. I guess I think that's. I don't. It gave me a symbol on my calculator, but it's capital M with like a line off the branch.
So when you do 100,
So I think that's either.
so I know what you're trying to do. So let me see if I can correct this real quick.
There we go. 3.7 million. There we go. My calculator was good.
Yeah, fix and say if you say 100 divided by 27000, you should get 3.7 milli.
Yep. Okay, cool. No, I just did my calculator wrong.
It happens to the best of us. All right, so what about finding resistance? If I have 30 milliamps with 15 volts, what is my resistance?
Would that be 50K?
So 30 milli times 15 volts, 15 volts divided by 30 milli should give you
30 milli would be 0.00030, right?
no, it'd just be 0.03.
Okay. Makes more sense. 15 divided by 0.03 would be 500.
It'd be 500 ohms.
Yeah.
500 ohms even. All right.
It'll take me a minute to get back into the groove of doing that. Whatchamacallit? I forgot the word you used for it in intro. Conversions. That's it. It's gonna take me a minute to get back to the conversions.
So with voltage constant, when current increases, resistance decreases by the same ratio. So what that means is that, let's see if this, let me draw it. Here's my fulcrum on a seesaw, right? We're going to call this voltage. And then we have resistance on one side and current on the other. Okay? So if I put more pressure on current, what's going to happen to my resistance?
Can you repeat that one more time?
So if I give more current, I have less resistance. If I have more resistance, I have less current, as long as my voltage does not move around on my scale.
Yeah.
Does that make sense to everybody?
Yes, ma'am.
So this is the ratio proportion right here, is that when one goes up, the other goes down. And then when this goes up, this goes down, as long as my voltage is not changing. Okay? As long as your voltage doesn't change, your resistance and your current are inversely proportional. When one goes up, the other goes down, vice versa. With the resistance held constant, if voltage is increased, current must also increase by the same ratio. With resistance held constant, if the current increases, voltage has to increase by the same ratio. So in other words, if R does not change, R is on the outside, when V goes up, I goes up. If I goes down, V has to go down too. So they are directly proportional. Does that make sense?
Yes, ma'am.
So with current constant, if voltage increases, so we're going to pull I off here, because the same thing occurs when you have V increase and you want your current to stay the same. Your resistance has to increase by the same measure. So if you double your voltage, you have to double your resistance, or your current will skew out. However, if voltage drops, you need to be dropping your resistance as well, or your current will again do something different. Okay? So if voltage is going down, current goes down. If voltage goes up, current goes up, as long as your resistance remains the same. Okay? That's only if your resistance does not change. And the same thing, so this is where you get to see the teeter-totter effect here, the seesaw effect. When voltage increased and current increased, when my voltage and current are set, I've got 10 ohms. These are my voltage and current. When I increase my resistance, my voltage does not change, my current drops by half. If that makes any sense, the way I was saying that. So we use the term proportional. This means that two numbers are, if you have two numbers or more, if one changes, the other changes. They will go hand in hand. Directly proportional means that both numbers will move in the same direction. So again, if you have resistance or current that is held constant, then voltage and whichever the other one is, when one goes up, the other goes up. And then you have inversely proportional. This is the relationship between current and resistance, whereby if your current decreases, your resistance increases. If your resistance decreases, your current increases. So you have what are called variables and constants. Again, this should be kind of a familiar term for y'all. Y'all probably learned it in elementary and middle school. So you have what are called variables. This is a number that changes in a math equation, while a constant is a number that does not change. A lot of electrical equation consists of three terms or numbers. So if you have two of those three numbers, one is considered the constant and the others are considered variables. That's how that works. Okay. Linear proportional resistance is directly proportional to voltage, inversely to current. This is all just repeating myself again, so y'all got any questions on this before we keep going?
No, ma'am.
Okay. So as voltage increases, if resistance does not change, your current will increase. So here's some more Ohm's law. We have 10 volts and 100 ohms. What is my current? Hmm? So we have 10 volts divided by 100 ohms. It should give you 10 milliamps, I believe you said.
Yeah.
It's 100 milliamps.
Yeah. I just put that in right. You said 100 milliamps. I confused myself.
So what would be the value of your current if your voltage doubled?
It'd still be 100.
If resistance remains the same, when you increase voltage, what happens to your current? If I change this to 20 volts,
And change resistance to 200.
nope, resistance will remain the same.
Oh, okay, yeah.
If I increase my voltage to 20, my resistance stays the same. I would end up 200
milliamps. I was thinking since it doubled your voltage, you had double your resistance.
Not quite. You don't have to, unless that's what you're trying to go for.
Okay. That's why I still got 100, just because I thought both of them had to increase at the same time.
No?
Okay.
Again.
No.
So what is the value of my current if I half my resistance from the original value? So instead of 10 volts, I have 5 volts. Same resistance, what does my current end up being?
50 milliamps.
50 milliamps. Does that make sense to everybody?
Yes, ma'am.
All right, so let's look at this one. We have 100 volts, 20 ohms. What is my current?
Five. 5 even. 5 amps.
All right, so what would happen to my current if my resistance doubles? So if I take my resistance and bring it up to 40 ohms,
It'd be 2.5 amps.
and what would happen to my current if my resistance was halved from 20 to 10?
It would go up to 10 amps.
That makes sense to everybody?
Yes, ma'am.
All right. So here we have 5 amps and 100 ohms. What is my voltage?
It'll be 500 volts.
Be 500 volts. What would be the value of the source voltage if your current doubles? So if my current goes up to 10 amps, what's my voltage going to do?
It'd be 1 kilovolt.
Be 1 kilovolt? No,
Yes, ma'am.
correct.
Basically, if the amps double, then the voltage double, basically. If the resistance stays the same.
Very good. So does that mean they're directly or inversely proportional?
They're directly proportional.
They're directly proportional. So what would happen instead if my resistance, instead of my current, my resistance went to half? If instead of having 100 ohms, I only had 50 at 5 amps, what would my voltage be then?
It would be 250 volts, 2.5.
So are they directly or inversely proportional?
They're directly proportional.
They're directly proportional. All right. What about this one?
Be 330 volts.
Are you sure it's not just 33?
Milliamps would be 0.0 to 0.01, right?
Yes.
And
that's
3.3K would be 33,000 or 3,300.
3,300.
Okay, that's where I'm. Yeah, it'd be 33 because I put 33,000 instead of 3,300. I know where I messed up.
Okay. So what would happen if, well, we've already covered that anyway. So what about this guy right here?
It would be 4 ohms.
Okay. What will be the resistance if the voltage doubles and the current remains the same?
The resistance would double.
Your resistance would double. So if this goes to 24, that doesn't change, I would end up with 8 ohms.
Yep.
All right. What would happen to the resistance if my voltage is the same, but my current halves to 1.5 amps?
It would double again.
So go up to, it would stay at 8 volts, right?
Yes, ma'am.
Okay. Y'all want to take a break real quick? Do about a 10-minute break?
Yeah, that'll work.
All right, let's take a 10-minute break, guys, and then we'll come back and get some more of this done. And then we'll call it out for the day. Got about a little bit more to go. So energy is the fundamental capacity to do work, measured in joules. And power what we call power is the rate at which energy is used. We measure that in watts. And power is equal to energy divided by time, or force multiplied by speed. How does this apply to us? Well, if you look at your meter on your house, what it's doing is it's accumulating how much power you use over time. So let's say you use 1,000 kilowatts of power in 1 month. That's what you are billed for by the power company at the end of the month. So Watt's law, it should look familiar because the only thing that's really changed is the fact that instead of R, we have P. And P has taken the place of V in this case. So we start off with power is equal to current times voltage. So if we look back here, we have force times speed, force, speed. Quite literally, force times speed. If I'm looking for my speed, if I'm looking for my current, I divide my power by my voltage. If I'm looking for my voltage, I divide power by current. Does that make sense?
Yes, ma'am.
Okay. So power used over time, or power consumption, is watt hours. It is found by multiplying the power used by the time in hours. And like I said, this is how the power company gives you your bill. Now, one way people have tried to save money is by, they say the best way to save it is to turn off everything and unplug it. That means that you no longer have power being consumed. It's one of those, it's a catch-22 in this case, because let's say you are super uber needing to conserve energy. So one of the best ways you could do it would be to go downstairs in your basement and flip your main breaker so that you're not using any power. The big main breaker would turn off all power to your house. However, should you do that, your refrigerator will most likely stop running and your food will spoil. That, or if it's summer, your house will be sweltering hot when you get home, or you might find icicles all over your house if it's super cold. But most people, what they do in order to save a little bit of money is to unplug everything as far as chargers and stuff go at the end of the night. Or I'm sorry, before they leave for the day, and make sure all the lights are turned off. And that does save money. You can actually start by looking at appliances, and on most appliances, when you buy them, they will tell you how many watts of power they use, and you can figure out yourself how much power they're going to consume based on your usage. So, food for thought. So the biggest thing about anything that is able to take current and create work is a lot of it throws off a lot of heat. That's why if you've ever tried to grab hold of a light bulb you just turned off, you might lose a fingerprint or two, because it has converted that current and that voltage into a into heat energy as well as light energy. Excuse me. So we convert any and all energy into either heat energy or light energy when we're dealing with this. That's what dissipation's about. Now, there are a lot of formulas for Ohm's law, and there's a reason I didn't teach it to y'all to begin with. And that's because it gets a little overwhelming when you first start glancing at it. But here's what you have. You have your voltage, which is I times R, P divided by I, or the square root of P times R. Resistance is fairly easy. You either square I or you square V. Yep. Current is the square root of P divided by R, P over V, or V over R. And then you have watts, which is V squared R, V squared divided by R, I times V, and R times I squared. These are all different formulas. Yes, they are not as easy to memorize. The main ones I would recommend you memorize are the ones that are the square roots. So square root of P divided by R gives you I, or the square root of P times R gives you V. Because sometimes a math problem will not give you V or I, they just give you P and R. If you have P and R and you have these two right here memorized, you are gold. Again, here's the big Ohm's law wheel. And again, E is the same as V. The only thing it means different is that instead of calling it voltage, we're calling it an electromotive force, which is a mouthful. All right. Almost all electrical electronic components are rated in something. Overcurrent protection devices are rated per volts and amps. Volts and amps. If you look on any fuse or any circuit breaker, it tells you how much current it will allow and how much voltage it will allow. If it's a circuit breaker, there's a couple of different voltages you'll probably be dealing with. The most common one is 120, which basically is like a 110, 120 voltage. The second one is semi-common, is 240. That's the truly major appliances in your house. Ones that have really funky plugs. Make sure you're not trying to plug a 120 into a 240. Conductors are rated in amps and ohms per 1,000 feet. Okay. Because the funny thing about conductors is, yes, they conduct electricity, but are they ever truly efficient? No. Matter of fact, light bulbs are made with nothing but conductive material. The filaments in an old Edison bulb are actually conductive material. It's just wound really, really a lot. And that winding allows for heat energy to build up, as well as the hotter that wire gets, the more resistive it becomes. Hmm? It's wound up in a coil so that it creates a more resistive environment for it. But truthfully, if you ever really look at one of those filaments, it's a piece of wire. Yeah, you're just dealing with a piece of wire in a light bulb. So essentially, you're looking at something that is rated for current and resistance. There's probably a resistor somewhere in that to help with the resistance of the bulb, but its resistance is probably very tiny because the more current you have through that bulb, the brighter the bulb gets. Speaking of bulbs, the incandescent light bulb is rated in voltage and watts. And insulators are rated in volts and the environment. So. Resistors are rated in ohms and watts. And truthfully, everything that you work with is going to have a given tolerance of some sort, just because nothing can ever be completely spot on. There's always just a little bit of wiggle room with anything. If you've ever had to manufacture anything in your life, you know that it is impossible to get the same thing perfect every time, unless you're a robot. And even then, those can you can have faulty materials that come through and end up in your batch. It's not the fault of the manufacturer, it's the fault of the process. That's why most manufacturers will actually take the old stuff and scrap it, start over, if it starts getting faulty. The ohm intolerance of resistors between 1/8 and 2 watts are given using either a 4 or 5 band color code, which we've gone over. The ohm values of resistors above 2 watts are usually stenciled onto the resistor, because a 2-watt resistor is fairly sizable. Just to kind of give you an idea. So you have 1/8 of a watt, which is about the size of an ant. You have a 1/4 watt, it's a little bit bigger. Half, 1, 2, 5. You get 10 watts, 20 watts, and you've got those two are ceramic. But if you notice, you still have the color bands on a lot of the bigger ones. But once they get this size, they start stamping it on. Okay. But yeah, the 1/8 is about the size of an ant. They are T90. So ohm values of resistors above 2 watts. I already said that. Never mind. So it should look familiar. This is your resistor color code. You will never have a resistor that starts with gold, silver, or black, because you do not start with a negative number and you do not start with a 0. And in between that, you have brown, red, orange, yellow, green, blue, violet, then gray, and white. Where gold and silver tend to come in a lot is the multiplier bands, where you're multiplying by 0.1 or 10 to the negative 1 for gold, and for silver it's 0.01 or 10 to the negative 2. Then we get to tolerance bands. You have brown 1%, red is 2, 0.5, 0.25, 0.1, 0.05, 5%, and 10%. Okay. So the power rating is the maximum amount of power that a resistor can dissipate without damage. So just like a light bulb, if you put a 25-watt light bulb in a 50-watt socket, what's going to happen? Probably blow up the bulb. It's never good. Don't do that. So it can handle up to 25 watts. If you go over 25 watts, that bulb will blow every time. The power rating is determined by the physical characteristics of the resistor, and these are length, material, and circumference. Basically, the physical everything about it will tell you what it can handle and what it can't. So how long is it? How wide is it? What is it made of? And these are not to scale, because like I said, the eighth of a watt is the size of an ant. They are not that big. All right, so we have wire wound, we have carbon films and things like that with these. Wire wound resistors have a larger power rating, 1 watt to 225 watts. If you've ever seen an overhead crane and you see the big resistor box to it, there are some of those resistor boxes that are about 5 feet tall plus. And what is that for? It's because the wattage draw whenever that crane first starts moving is so massive, you have to have a resistor in between it to make sure that it doesn't overheat the crane or damage anything else. A locomotive dynamic braking resistor can be as high as 3 kilowatts. A room heater and a water heater elements can be as high as 6 kilowatts. What this essentially is that it's wire that is wound around in a coil and essentially just used as a heating element. Because the longer a piece of wire is and the more electricity you put through it, the hotter the heat is. If that makes any sense. Yeah. So this is very similar to what I'm talking about. Is if you look at this right here, or if you look at the elements of any real heater, that's all wire. And the voltage and current put through it create heat. So when you're selecting the proper resistor, you have to be careful. You want to select it for the next largest size above the calculated power you're going to have. So let's say, look at the voltage source in the 120. So 10 divided by 120 should give you what? My I on here equals 83.3 repeating milliamps. So then I can take that number multiply it by 10, and my power rating is 833.3 milliwatts. All right, so decision time comes up here. We already know the general power ratings. Let me get back to that right now. So would an eighth of a watt work here? 0.125? Nope. Would a half watt? So I would have to go up to a 1 watt resistor to be able to sufficiently work with this resistor, with this power rating. Okay. So this one again gives me 10 volts here. Gives me 100 milliwatts. So I would be able to use a 1/8 of a watt, since this is 0.125. That's essentially all you have to really do, is you have to look at what is the wattage this thing will use and what's the most compatible. Now, do I want to always go grab a 2 watt resistor? Not if I don't need it. The whole reason I grab an eighth of a watt is because I'm trying to put it in a smaller area. Okay, you want things to always be more compact. That's why smartwatches work and things like that, is you have more compact components. It's not going to draw a lot of power, not going to use a lot of power, so what's the point of having something massive and something small? It really isn't. So looking at this, they're asking which one will be damaged. So we're given voltage and we're given resistance, and we need to find power. Going back to our Ohm's law wheel, if I have voltage and I have resistance, I can find power by using V squared divided by R. So what is A? What is my wattage at A?
Eight hundred and ten milli.
That's a lot of power. Now what they've got here is a 1/4 watt resistor. Is that big enough to deal with 810 milli? Nope, it'll fry it out. So looking at the next one, 24 volts, 1.5 kilo ohms. What's my wattage for B? Should give you
384 milli.
384 milliwatts. We have a 1/2 watt resistor. Is that big enough?
Don't think so.
So 0.384
Oh yeah, it'll
versus
be
a
enough.
0.5.
Yeah, it'll be enough actually.
That one's good. So then lastly, we have this guy. We have 5 volts and 10 ohms. What is my wattage? 2.5.
I was just about to unmute my mic and say that.
So is a 1 watt resistor going to be able to handle 2.5 watts of power? No. So the only one that would be safe is B. Does it make sense? So A and C will be damaged. B will be unharmed. He's just big enough. He's going to be okay. All right, we'll talk about series circuits later, because this is starting to get into series circuits. All right, so if y'all got any questions for me, or anything y'all want to address or ask about?
No, man. I'm all good.
All right, so like I said, this was just kind of a quick review of Ohm's Law. We'll get into new stuff on Wednesday. Make sure y'all are ready for that. And it's going to have to do with what's called series circuits. You've actually done a few experiments with it, but we're going to get into it some more. Things I need y'all to do is get your first week quizzes and agreements done. Get your lab book ordered. I want to get into labs sooner rather than later. And lastly, we are going to be having classes on campus almost all the time, so make sure you're here, guys.
Yes, ma'am.
Because that way we can go to lab and be hands-on and do stuff that's not available and ready to do through Blackboard.